Hi, my name is Mehdi Eskandari-Ghadi, and in the next few minutes, I will share with you our most recent findings regarding the initial shrinkage of microporous material upon adsorption. The reason we like to study this topic is that adsorption deformation is everywhere. In nature, pine cones and wheat awns mechanically open up to release their seeds when they sense humidity. The driving force behind this is known to be adsorption swelling. In engineering, clays swell up to 10% and even more when they take in water. This kind of phenomenon can be taken advantage of to engineer gas sensing actuators. The occurrences of adsorption deformation is countless. Has the phenomenon been explained? Partially, yes. Banham attributes surface tension to adsorption swelling. Consider a balloon with surface tension gamma acting on its surface. What happens if gamma is reduced? The balloon is allowed to expand. Now consider this porous material. Think of the pore walls as balloons encapsulating the material inside. Banham explains that as absorption takes place, the surface tension on the pore walls is reduced, thus allowing the material to swell. This concept has been used to predict quantitatively the adsorption swelling experimental data. However, both earlier and recent results show that in micropores, there is an initial shrinkage region at very low pressures prior to the overall swelling. This brings us to our first objective. Can we explain initial shrinkage of microporous material through pore mechanics? Before we delve into micropores, let's look at larger pores for a second. If the pore walls are sufficiently far enough, there is a region between the pore walls that exhibits bulk fluid properties such as bulk fluid pressure. However, as you bring the pore walls closer and closer, the adsorbed layers start to overlap, and at that point, there is nowhere inside the pore that has bulk fluid properties. This overlap is accompanied with the interaction of the adsorbed layers that gives rise to additional forces commonly known as discharging pressure or salvation pressure. The existence of these additional forces means that additional work is required to change the distance between the two surfaces. In order to incorporate all of this into our pore mechanics framework, we take the free energy of the surface phase in the larger pore and we add to it the additional work that's necessary in micropores. If you follow through the thermodynamics, you can derive the internal energy of the entire fluid inside the pore and compare that with the case of the larger pores. We immediately notice that in micropores, the pore walls don't feel only the bulk fluid pressure, but the bulk fluid pressure plus the disjoining pressure. Also, the surface tension is modified by a disjoining pressure term. Furthermore, thermodynamic derivation gives us the surface forces in terms of the adsorption isotherm. So all we need to compute the surface forces is an adsorption isotherm in terms of the bulk fluid pressure P and the pore width H. But hold that thought. How do the surface forces on a pore level upscale to the continuum level to be incorporated in a pore mechanics framework? We follow standard procedure. The pore mechanics framework developed by Biot and Kusi takes only a solid and fluid phase into consideration in a theory of mixture. Zhang extends that theory by considering a surface phase in addition to the solid and fluid phase in the theory of mixture, and develops a so-called surface pore mechanics framework. From that point forward, we can get the Clausius-Duhem inequality, which can be decomposed to give us the mechanical dissipation. With the fluid and surface free energies known, we can derive the solid free energy of the microporous material. It's the consideration of the surface phase as an independent phase in the fundamental theory of mixture that allows us to naturally recover these terms in the solid free energy. The solid free energy can be visualized as such. The mean stress is conjugate to the volumetric strain. The shear stress is conjugate to the deviatoric strain. The energy conjugate to the porosity, which would be the pressure that the inside of the pore walls are feeling, is P plus pi. And we have the modified surface energy conjugate to the surface area. It seems that we have four deformation variables: epsilon, E, phi, and AS. However, AS is not an independent variable. The same deformation variables that take our original configuration to the new configuration also take the old AS to the new AS. Therefore, changes in AS must be a function of changes in the deformation variables. Therefore, we can rewrite our solid free energy as such. This form is particularly convenient because it allows us to write our constitutive relations like this and also define our adsorption stresses and adsorption pressure. You can think of the adsorption stresses and pressure as analogous to the pre-stress in concrete. Consider a concrete rod with stress sigma applied to the two ends and a rebar in the middle pre-stressed to delta sigma A. If you increase the pre-stress level, what happens is that the rebar, the concrete rod, shrinks. And the force deformation relationship looks something like this, which is similar to what we have above. Okay, so to complete our system and test our theory, we need a couple of ingredients. The first one is the free energy of the porous solid, for which we select the most simple case, isotropic linear pore elasticity. The next ingredient is a relationship between the pore area and the deformation variables. For that, we use the spherical pore model. The final ingredient is the adsorption isotherm, and as you may recall, this defines our surface forces. So it is a key to the behavior of our model. So after going through a couple different adsorption isotherm models, we found the BDDT model suitable for our purpose. The BDDT model is based on the BET model, which is well known, and the BET model gives the amount adsorbed on a free surface as a function of the bulk fluid pressure, while the BDDT model gives the amount adsorbed between two surfaces as a function of the distance between them and the bulk fluid pressure. The resultant surface forces look like this. An initial attractive disjointing pressure suggests initial shrinkage, while an overall negative surface tension suggests swelling. Obviously, there is a competition between them, and the question is who will win this competition. I think a phase diagram kind of figure should illustrate this best. The vertical axis here is a relative pressure, and the horizontal axis represents the pore width. The different curves are for different model parameters, but what's in common between them is that there is a region in small pore sizes and low pressure where the material exhibits contraction or shrinkage. And if you have larger pore sizes or if you increase the relative pressure, you enter the swelling region. So in regard to the first objective, we have shown that the attractive disjointing pressure can qualitatively explain the initial shrinkage of microporous material. But what about the quantitative part? Consider this set of experimental results. On top, we have the pore size distribution data, and on bottom, we have the adsorption and deformation data. We now know that in order to capture the initial shrinkage in the deformation data, we need a micropore size. So because of that, we select the dominant micropore size from the pore size distribution to give to our model. We feed our model with physical parameters, and for those parameters where physical values don't exist, which are just a few, we calibrate them. The result looks something like this. So the model does a good job in capturing the deformation, but not so well in capturing the amount absorbed. However, in regards to the first objective, we have shown now that the attractive disjointing pressure can also quantitatively explain the initial shrinkage in microporous material. But what is the problem with the amount absorbed? We think that the choice of pore size is so small that those small pores are immediately filled to capacity and adsorption stops. But we need those small pore sizes to capture the initial shrinkage in the deformation data. So here's an idea. Let's, instead of having just this one small pore size represent the entire pore size distribution, let's also consider all these larger pore sizes that can continue to adsorb. So we have our second objective here. Can we predict the deformation and adsorption by considering the entire pore size distribution data? In order to do that, we need to upgrade our model. We start with the free energy of a single pore network and make as many copies of it as we would like to get the free energies of many pore networks, each of which can have its own pore size. By summation of them, we get the free energy of a many pore network. And along with it comes natural averaging relations that give the surface forces on the level of pore network in terms of surface forces on the level of single pores. Now, instead of having a pore size distribution where 100% of the pores are of this small size, we select 107 different pore sizes to represent the entire pore size distribution. The results look quite satisfying. In terms of the second objective, we are done. We believe that we have captured the physics of the transition from initial shrinkage to the overall swelling in microporous material. Along the way, we've learned that the consideration of pore size distribution is important, and we are continuing this study by investigating how important it is to consider the pore size distribution. Thank you for listening. If you are interested in this topic, you can refer to the two references below, and the most recent findings that we have had is published in the first reference below.